Everyone. So we're going to go through 5.6 and 5.7. Thankfully, 5.6 is very short. And also what I'm going to do is literally just go through the homework. I think that might be the easiest way going through all this. So let me just kind of get this set up. 5.6 centers around this idea called L'Hopital's rule. And so we're going to figure out finally how can we make our limit life easier now that we know derivatives. And the big worry is that you're going to look at this and essentially say, I cannot believe you did not teach us this earlier when we were learning about limits. Why have we not seen this until now? Now, there is another question, and here's the question I have. Why is this showing up in the middle of chapter 5, which is all about integration? And the answer is, I don't know. This is a really weird way to lay out this. Usually you look at this in derivatives, since actually we're not going to be doing any integrating, we're just going to be using derivatives. But I'm sure there's a reason they did that. Anyways, the idea is the reason this couldn't be done before, or while we learned limits, is because limits make derivatives possible. That's the key argument there. We can't talk about a derivative or use a derivative process if we haven't essentially proven why limits can be trusted to get us derivatives. But it's, kind of like we've gone this far in the course. We think limits can be trusted. We've done a lot of derivative work. We've done a lot of integral work. Both of those rely on limits. So now that we know them, can we find a better method to solve our limit questions? And the answer is, of course, yes. Okay, so first let's look at number 1 here. Number 1, what we learned to do is if we've got the limit as x approaches 0, sine of 7x over 9x, what we learned to do is we learned to say, well, I can't evaluate this right now because the inside of my trig doesn't match the underneath divisor, but maybe I can do some clever algebraic manipulation. Maybe what I can start doing, still have a limit, maybe I can push out that 1/9 and deal with it later. And this is a technique we've seen in integrating and deriving. We've kind of talked about this as a class, that number multiplying outside of a function could just be saved for later, so to speak. And now what I want to do is, again, I want to get a 7 on the bottom. So in other words, I moved the 9 because 9 and 7 don't really work well together, so let's move it out and get it out of the way. But I do need a 7 on the bottom. What can I do? Well, I can multiply this fraction by 7 over 7, but I'm going to cleverly place my 7s. And that is x approaches 0 of, well, I'm going to put the 7 over the 9 for the numerator. But for the denominator, because all we're doing, although there's trig right now, all that's going on here is a fraction multiplying to a fraction. All that's going on is multiplication and division, and we can do that in any order. So I did multiply this whole thing by 7 over 7, but I'm just cleverly choosing to write the numerator's 7 out front along with that 9 that doesn't work nicely, and the other 7 into the denominator, because eventually these will all multiply, or eventually those 7s will cancel and the 9 ends up back with x. But crucially, what I have now is I have sine of some algebra structure over its algebra structure. Both of those structures approach 0 as x approaches 0, and we get this very famous limit which says this must be 7 over 9 times 1. It turns out that sine of some function over some function, when both of those approach 0, this whole thing becomes 1, so we get 7/9. So they say use techniques from chapter 2 and 4, you get 7/9. I mean, the weird thing is we're going to get the same answer either way, but it's definitely going to look different. So it's time to learn about L'Hopital's rule. So L'Hopital's rule has a few steps. So I'm just going to write L'Hop steps. The steps are this. 1, establish indeterminate form. And namely, that's going to be 0 over 0 or infinity over infinity. And when you get into your later calculus classes, you'll learn that there are many other indeterminate forms. But for now, we're just going to focus on these two. So we're going to establish indeterminate form. We are then going to derive the numerator and denominator individually and place them in a new fraction, and And then 3 is retry the limit. All right, so let's see this in practice. So let's relook at number 1, the limit as x approaches 0 of sine of 7x over 9x. Well, if I directly substitute, that would just say sine of 0, and that is indeed 0, and 9 times 0 is 0, so I do get 0 over 0, which is indeterminate form. Now, I definitely can't continue this with an equal sign because indeterminate form is its own special thing. 0 over 0 doesn't equal anything but the name indeterminate form. So I can't link this, so to speak. We sometimes call it a linkage error if you then write equals and then continue the process. And more so, this is like really nitpicky for AP, but you know, I do like their precision of how they write the statement of, okay, we got 0 over 0, call that indeterminate form. Now let's say that we're going to apply L'Hopital's rule, because I must establish indeterminate form. Now I can go through what it says. And so now I'm going to derive the numerator and denominator individually. And students usually make a few errors here because they're used to seeing a fraction and doing the quotient rule, which you should do if the question says derive this thing. But the question isn't derive this thing, the question is find the limit. And because the limit first evaluates the indeterminate form, I can use L'Hopital's rule, which again says, I know this is a quotient, but you're trying to find a limit. So let me derive the numerator, which would have a little bit of a chain rule to it. It would be 7, the inside derived, times sine derived, which is cosine with its original inside contents, over 9x derived, which is 9. So I derive the numerator and denominator individually, not as a quotient rule, because the question wasn't derive this, the question was evaluate this limit, and we're doing some tricky derivative stuff to do so. And then place them in a new fraction. There they are. And that's what I mean. The numerator should still be the numerator, although it's the derivative. The denominator should still be the denominator, but it's the derivative. And bring back the same limit question. And we get a really interesting result this time, because this time, when cosine of 7x, or when x approaches 0, that's going to say cosine of 0, but cosine of 0 isn't 0 this time, it's 1. So look what I get. I get 7 over 9, and I don't need to memorize that special limit rule. I don't need to cleverly manipulate the 1/9 and the 7 over 7. I get my answer really simply from one evaluation. The other variable even disappeared. So that's really cool that we can get the same answer via derivatives. And what we're going to do now is just run through L'Hopital's rule for the rest of these, hopefully somewhat quickly, because YouTube only lets me upload 15 minutes at a time. Okay, so of course, the first step begins by evaluating our limit and making sure we do get indeterminate form. So I'm just going to do that myself kind of out loud. So 7 squared is 49. Minus 3 times 7 will be minus 21, and then minus 28. So the numerator is indeed 0. I know that that's true. And the denominator is definitely 0 as well. Now, also just to say out loud, 7 times 4, right? 7 and 4 do multiply to 28, but subtract to 3. So we could just do this as a limit by factoring question. But essentially, I've said out loud this is 0 over 0. So I have established that I get indeterminate form, and I'm going to apply L'Hopital's rule. And so that means I can now write this as 2x minus 3 over just a simple 1. And now when I plug in 7, I get, let's see here, 14 minus 3, which is 11 over 1. I get 11. All right, awesome. Just to verify that, let's show you what it looks like when we do this by factoring. You would get an x minus 7 times an x plus 4. That's how you multiply the negative 28 and combine the negative 3. Your x minus 7s would cancel, and look what you get when you plug 7 into the remaining algebra. You still get 11. So L'Hopital's rule is doing some really cool stuff. Again, be careful. I wouldn't just start writing this. I would first establish that I get 0 over 0, then proceed. All right, 2 more a little bit more quickly, and we've gotten infinity this time. So first we have x approaching infinity of x cubed over 5e to the x over 2. And when I plug in infinity, well, that's going to approach infinity over infinity, which is, of course, indeterminate form. Okay, what happens this time after we apply L'Hopital's rule and try again is we get 3x squared from the numerator, and the denominator is going to have a 1/2 pop out via the chain rule, and I get e to the x over 2 again. Now I actually still get infinity over infinity, which is indeterminate form. So I'll apply L'Hopital's rule again, and we're going to do this maybe a few more times. Now I get 6x over 5 over 4 e to the x over 2, which is still infinity over infinity, which is still indeterminate form, but thankfully we're going to see something different on this very last run. Here we go. Finally, I see 6 over 5 over 8 e to the x over 2. And finally, this is not infinity over infinity. This is 6 over infinity. And that is not indeterminate form. That is 0. And we actually kind of investigated this a little bit earlier. We said this earlier, way long ago, with infinite limits. The idea is that an exponential is always going to grow faster than a polynomial eventually. And actually, L'Hopital's rule shows us why. It shows us that, well, a polynomial is eventually going to derive away or remove the algebra, and it won't have any more variation to it. But the exponential is always going to remain and always going to keep on growing. So eventually the polynomial doesn't grow as fast as the exponential. So eventually the denominator becomes huge and the numerator remains small relative to that huge denominator, and we approach 0. All right, we've got one more example and then one more really important point to make. Let's look at this next one. Trust me, when I plug in infinity, that is going to be infinity over infinity. So I'm going to start with my first applying of L'Hopital's rule, but I did establish that I do get infinity over infinity first. Okay, be careful here because when you derive the numerator, ln of stuff via the chain rule derives to inner derivative over inside. So there's the numerator. The numerator itself derived to a fraction, and my denominator will be 5x to the 4th. Now, before I evaluate that, let me clean this up a little bit. That's going to be 3 over x divided by 5x to the 4th. I can clean that up a little bit further. That's going to be 3 over 5x to the 5th. And I can actually evaluate that now. That's 3 over infinity, which again is going to approach 0. So it looks like both of these approached 0. And let's submit. Well, I forgot to answer that one, but it's 11. Cool. Yay, I just got 100 on my first homework of the course. All right. One important thing is to show why 0 over 0 matters so much in a really quick example. Let's do, again, just a simple one. Let's say we had the limit as x approaches, I don't know, 2. And also, I don't want you to be confused while we kind of had this example. You can have a limit that isn't 0 that still gives you 0 over 0. So it's not the 2 that's going to cause the issue. It's something else. Let's say I had x squared minus 5 over 3x plus 7. So if I do direct substitution here, I would actually get negative 1 over, let's see here, 6 plus 7 is 13. Now that is my limit because by direct substitution I get an answer. So all I'm going to do real quickly is just show you this is why getting indeterminate form is such a crucial step for L'Hopital's rule. Because if you evaluate this directly and don't get 0 over 0, look at what happens if you blindly assume that now that I know L'Hopital's rule, I can make all my problems a little bit less complex by dealing with smaller exponents. Well, let's say, again, you incorrectly apply L'Hopital's rule because you think you can just blindly use that whenever you want. Well, that would be 2x over 3, and look at what I get when I plug 2 in now. I get 4/3. Those are definitely not the same, and this is the correct answer because this is what I get from direct substitution. If direct substitution works, it should always be done first. Or if you don't know if direct substitution fails, it gives you indeterminate form, you must try it first and see what you get. Only after you get 0 over 0 or infinity over infinity can you go about applying L'Hopital's rule or doing other algebraic techniques. But if you get an answer off the bat, there's no reason to do L'Hopital's rule, to do limit by factoring or any other work because your answer's already been found. So now that being said, if you do some factoring work, if this could factor, you would still get negative 1 over 13. The key here is, though, if you don't get indeterminate form, applying L'Hopital's rule gives you a nonsense answer that is not the true answer, which is a little bit interesting the first time you encounter that.